So the next topic we're going to cover is weak acid titrations, and these are similar in a lot of ways to the strong acid titrations we covered in the earlier in the course, but there's some differences as well. And the differences mainly have to do with the fact that rather than dissociating completely, these weak acids, as we've learned, have an equilibrium. Okay, they exist in equilibrium between the undissociated acid and the H3O plus and conjugate base. And so that has an effect on the pH as you're adding a strong base to it. And so let's start off by looking at just the different types of titration curves from the outset. So this one right here would be possibly, we have a solution of HCl and we titrate it with sodium hydroxide. Okay, so what's going on in this portion is with the HCl is being neutralized by the hydroxide. Okay, so in this portion we have HCl is being neutralized by hydroxide, but we have some HCl left. In other words, in this portion we haven't neutralized all the HCl. Then all of a sudden it jumps up and then over. Okay, the midpoint to this curve, which will become important later, for a strong acid with a strong base, would be a pH of 7. Okay, now compare that to what this weak acid curve looks like. First of all, we'll have a starting pH that's a little bit different. It's going to be a little bit more curved. Okay, and the thing I want you guys to note is this center point right here is going to be at a higher pH. We're going to learn why that is, in just a second. And then after this point, these two curves match up perfectly, and we'll talk about why that is too. So for right now, kind of realize that one of the main differences between these two is where the center point is. pH of 7 for a strong acid, titrated with a strong base, whereas this, which could be, maybe acetic, titrate with sodium hydroxide. Sodium hydroxide. That's what the blue one is here. Okay, its center point will be a little bit higher up. Okay, so what I want to do is, in your notes you can just have both these curves and, make it nice and big and write these. But I'm going to separate it in the slides so it doesn't get too cluttered. And let's start off with the starting point up until this equivalence point. So at the starting point right here, and let's do kind of the strong acid real quickly here. The starting point, the pH, depends on the concentration of the acid. Depends on concentration of the strong acid. So if I have a 1 molar solution of HCl, the concentration of the H plus will be 1 molar. I'd have a pH of 0, and so I would be starting at 0. Okay, for this one, it would be like a 0.1 molar HCl solution. But the point is the pH depends on the concentration of the strong acid, because that concentration would be the same as the concentration of H plus. Now for a weak acid, the starting pH, it depends, it does depend on the concentration, but it depends on really this Ka. Okay, so before I've added any base to this whatsoever, the pH that we have will be based on the Ka of the weak acid. So this is the problem, and at the starting point, this is the problem that we did in the last chapter. Hey, you have a solution of 0.1 molar acetic acid. What's the pH of that solution? And that would be the pH of your starting point. And then what happens, and this is what is kind of cool about this, at least I think it's cool. What happens is as I add, so I'm adding sodium hydroxide, okay? And as this happens, say I do, just for purposes, because it's quick to write, say this is maybe hydrofluoric acid, right? So as I add the sodium hydroxide, the acid will react with it, and it's going to form, not one, it's going to form the conjugate base, fluoride, plus water. And I want you guys to see this. At this point, after we've added some hydroxide, if we've neutralized some HF, we have a weak acid, and we have its conjugate base in the same solution. At this point, we have a buffer solution. Okay, so during this entire stretch right here, we will have our buffer solution. Okay, and the pH will depend on the Ka. So right here, the Ka, which is dependent on F minus an H3O plus, and HF. And in this region, we're going to have a concentration of both HF and F minus. Okay, and then that's going to in turn affect the H3O plus concentration. So as we're adding hydroxide, the pH is going up. Okay, this is going to get lower. This is going to start to go higher. This is going to get lower as well. And that's going to increase your pH, but it's going to be gradual. Then what occurs at these middle points? These middle points are what's called the equivalence points. And as I said, for a strong acid, this is going to occur at 7 pH, because what has happened at this equivalence point is all of this strong acid that I had initially has been neutralized and it forms water. Okay, and so, you know, what I would have if this was HCl, what I would have is I would have had all the H plus is neutralized exactly by hydroxide. I don't have any excess hydroxide. I don't have any excess H plus. All I have would be the sodium ions and chloride ions, both which are neutral ions. And so I have a nice neutral solution. Okay, I have a very rapid rise. Now, at the weak acid, okay, what I have at this equivalence point, which would be the midpoint, okay, it's a pH, let's just say the pH is greater than 7. And why is that? Because at this point, for a weak acid, I have just the conjugate base. Okay, I have just the conjugate base. So when I've neutralized all the HF and I have just the conjugate base, at this point, the pH will be due to the pH of a solution of fluoride ion. And so at this point, the pH is determined by the Kb of the conjugate base of the acid that you start with. Okay? So because of that, because it is a base, its pH is going to be above 7, so our equivalence point is going to be higher than 7. And then we have this really cool situation where if you go from where you start to the equivalence point right here, when you're halfway there, so say that this equivalence point occurs at 30, so when we're at 15, about right there, we've neutralized exactly half of the HF, and so we have equal concentrations of F minus and HF, and at this point we have the pKa is equal to pH, just like we had in that lab where we figured out what the Ka of a weak acid is. When these two concentrations are equal, the Ka, this H3O plus concentration, will be equal to the Ka. So this occurs at half equivalence point. So that's another important point too. So when we're thinking about this with a weak acid, we have a starting point which depends on the pH depends on the Ka of the acid. We have the equivalence point where the pH depends on the Kb of their conjugate base. We have the half equivalence point where the pKa is equal to the pH. And during this whole region, we have our buffer solution. All right, so you talked about what happens after the equivalence point. Okay, so we'll see by this side. And now past the equivalence point, notice how these two match up. Okay, so once we get past our equivalence points, these two graphs match up very well together. And the reason for that is in this region. So once we get past our equivalence point, what happens is we have excess hydroxide. And so the pH is determined by the excess hydroxide ions. Okay, so it won't be the total amount of hydroxide that we've added, but it will be the hydroxide that's left after we've neutralized all of our acid. Okay, so the excess hydroxide, and we can get the POH, and we can get the pH from that. Okay, by finding moles of the excess hydroxide that we've added. Okay, so we'll work on this during class, but those are that's the concepts involved with the pH curves, and to identify kind of a weak acid titration curve as opposed to a strong acid titration curve, look where they're starting, look at how rapidly they go up, and really look for where the midpoint is. Okay, and these are all telltale signs of whether something is a weak acid titration curve or a strong acid titration curve. That's about it. If you have any questions, please let me know.